Right now, somewhere beneath the surface of the ocean, there is a mountain range longer than the Andes, taller than the Alps, and wider than any chain of peaks on the surface of this planet, and we have never seen it. Not because we looked and found nothing, but because we never looked at all. We have mapped the moon down to the width of a single city block. We have mapped Mars in higher resolution than our own ocean floor. The ocean is not far away. It is here. It has always been here. And still, we know almost nothing about it. If you enjoy drifting into the deep ocean and discovering what lies beneath, please consider liking and subscribing. It truly helps more than you know. Are you ready? Let's begin. In 1959, a Soviet spacecraft called Luna 3 photographed the far side of the moon for the first time. Human eyes had never seen it. It had been there for 4.5 billion years, spinning silently behind the moon's near side, invisible from Earth, completely unknown. Within months, scientists had named its craters, mapped its highlands, begun building an atlas of a world no human had ever touched. At the time of that first blurry photograph, humanity had not yet sent a person to space. We had not yet developed the technology to travel beyond the atmosphere. Yet, we looked at a rock 384,000 kilometers away and started naming what we found there. That same year, less than 2 miles beneath the Atlantic Ocean, there were mountain peaks rising taller than Mont Blanc. There were valleys deeper than the Grand Canyon. There were plains stretching for thousands of kilometers, flat and silent and completely unmapped. Nobody named them. Nobody photographed them. Nobody was even trying. This is not a story about technology. It is a story about attention, about where a civilization decided to look and where, for reasons that are stranger than they first appear, it decided not to. Consider this. The moon is 384,000 kilometers away. To reach it, you must survive the vacuum of space, cosmic radiation, and the total absence of atmosphere. The journey takes 3 days. And yet, as of right now, the moon's surface has been mapped at a resolution of roughly 100 meters per pixel across its entire face. Some regions have been imaged at less than 1 meter per pixel, meaning you could navigate the moon's surface with a map the way you would navigate a city. Every significant crater has a name. The major mountain ranges have been cataloged. The geological history of its surface has been reconstructed across billions of years. We know the composition of its soil, the shape of its lava flows, the depth of its impact basins. We know the moon the way you know a room you have lived in for years. The ocean floor is right here. It sits beneath 71% of the planet's surface. In some places, it is less than 2 kilometers below the waves. The deepest point, the Challenger Deep, is not much farther down than a commercial aircraft cruises above your head. And yet, as of this moment, roughly 80% of the ocean floor has never been seen. Not at low resolution, not at high resolution. Never seen, never mapped, never described. This is not an exaggeration. When scientists use the phrase mapped the ocean floor, they are being generous. What exists is a rough model built primarily from satellite measurements of sea surface gravity, a technique that infers what lies below based on tiny variations in the ocean's surface caused by the gravitational pull of underwater terrain. It works at a scale of about 5 kilometers. 5 kilometers. To put that in context, the Titanic, lying 3,800 meters beneath the surface of the Atlantic, is roughly 270 meters long. On our best global ocean floor map, the Titanic does not exist. It is too small to appear. It is swallowed entirely by the resolution gap. An object nearly 3 football fields long, sitting on the floor of an ocean that covers 71% of this planet, and it does not show up. Compare that again to the moon. We can map the moon at 1 meter per pixel. We can see rocks, individual rocks, on the surface of another world at a distance of 384,000 kilometers. On Earth's own ocean floor, we cannot find a ship that thousands of people saw sink in the ocean that covers the planet we live on. Somewhere on the floor of the Pacific Ocean, there are volcanoes, not small ones. Volcanoes that rise 3, 4, 5 kilometers from the seafloor, taller from base to peak than Mount Everest measured from its own base. We know they exist because we have crossed their gravitational signatures. We have detected the ridges of their flanks with sonar, but we have not seen them. We have not mapped their peaks. We do not know if they are active. We do not know if something lives on them. They are there, enormous and silent, and they are invisible to us. There is a place in the Pacific called the Mid-Pacific Mountains. It is a chain of seamounts, underwater volcanic peaks, stretching for thousands of kilometers across the central Pacific Basin. Most of these seamounts have been identified. A small number have been visited. But when scientists look at the spaces between them in areas considered well surveyed, they find things. New seamounts, new ridges, structures that should have been obvious, that appear only when someone actually looks closely. In 2023, researchers using high-resolution sonar off the coast of Chile discovered a chain of previously unknown seamounts, one of them taller than a kilometer in waters that had been considered adequately charted. It was not unexplored ocean. It was the same ocean. Nobody had looked carefully enough. Until you realize what that means, the discovery sounds like good news. Scientists found something new. But that is not the point. The point is that we did not know it was there. An underwater mountain, over a kilometer tall, in a part of the ocean that had been surveyed, and it was invisible until someone decided to look more carefully. How many more are there in the parts nobody has looked at all? Here is a number that needs a moment. The total area of Earth's ocean floor is approximately 361 million square kilometers. Of that, roughly 26% has been mapped using modern high-resolution multi-beam sonar, the only method that produces reliable, detailed images of the seafloor. That means 267 million square kilometers remains essentially unseen. The total land surface of Earth is about 149 million square kilometers. The unmapped portion of the ocean floor is larger than all of Earth's continents combined. Not slightly larger, considerably larger. Every continent, every mountain range, every desert and forest and plateau on the surface of this planet, pile them together, and you still have not equaled the area of ocean floor that no human eye has ever examined. We have maps of Pluto. Let that land, Pluto, a dwarf planet, orbiting the Sun at an average distance of 5.9 billion kilometers, so far away that light from the Sun takes more than 5 hours to reach it, was mapped in extraordinary detail by the New Horizons spacecraft in 2015. We saw its heart-shaped nitrogen ice plain. We saw its mountain ranges of water ice rising 3 kilometers above the surface. We saw the texture of its surface in enough detail to identify geological processes never previously observed. We mapped Pluto in a single flyby, one spacecraft, one pass, and we know more about the surface of Pluto than we do about the floor of the ocean we swim in. This is the situation, not a rhetorical one, a literal, measurable, documented situation. The Moon, fully mapped. Mars, fully mapped, in higher resolution than our own ocean floor. Mercury, mapped. Venus, mapped through cloud-penetrating radar. The major moons of Jupiter and Saturn, mapped. Pluto, mapped in a single flyby. Earth's ocean floor, 26%. Until you hold all of that together, it sounds like an accident, like something that simply happened without anyone noticing. But it did not happen by accident. It happened because of choices. Specific choices made by specific people with specific amounts of money over several decades. And to understand those choices, to understand how we ended up knowing more about the face of Pluto than the floor of our own ocean, you have to go back further than the space age. You have to go back to the beginning of the mapping story itself. The Moon's story begins before the telescope. In 1609, Galileo Galilei pointed a crude instrument at the Moon and sketched what he saw: craters, mountains, the dark plains he called Maria, or seas. He did not know what they were. He had no way to visit them, but he looked, and he drew, and he named. The first modern lunar map, accurate enough to be scientifically useful, was produced by Johann Heinrich Mädler and Wilhelm Beer in the 1830s, from observations through a small refractor telescope in Berlin. Their Mappa Selenographica, completed in 1836, catalogued thousands of craters in meticulous detail in the 1830s, with a telescope and paper. And today, nearly 2 centuries later, that map remains largely accurate. The names stuck. The features are where Mädler and Beer said they were. When the space age began in the late 1950s, lunar mapping accelerated. The Soviet Luna program and the American Ranger and Lunar Orbiter programs spent years photographing the Moon's surface in preparation for human landings. By the time Apollo 11 touched down in 1969, scientists knew the landing site, a flat plain called the Sea of Tranquility, in extraordinary detail. They knew the slope gradients. They knew the boulder density. They knew the texture of the regolith, the fine powdery soil covering the surface. They were not guessing. They were landing on a surface they understood. The ocean floor has never received that preparation. No equivalent of the Lunar Orbiter program systematically photographed it. No network of spacecraft circled the planet, mapping its underwater terrain in preparation for some eventual mission to the bottom. The handful of deep-sea expeditions that have occurred in the past century were isolated, underfunded, and limited in scope. When the submersible Alvin descended to the mid-ocean ridge off the Galapagos Islands in 1977 and discovered hydrothermal vents teeming with life that required no sunlight, that rewrote the rules of biology the scientists aboard were not following a detailed map. They were flying blind. They found the vents by following a temperature anomaly in the water column. They had no idea what they would see when they arrived. There was no map to consult. That was not 1609. That was 1977. 8 years after humans walked on the moon. The Lunar Reconnaissance Orbiter, launched in 2009, has been mapping the moon continuously for more than 15 years. Its wide-angle camera has imaged the entire lunar surface at 100-meter resolution. Its narrow-angle camera has imaged approximately 12% of the surface at under 1 meter per pixel in detail so fine you could identify individual boulders. The total data archive of this single spacecraft exceeds 900 terabytes. 900 terabytes of photographs, elevation data, temperature maps, and chemical composition readings for a world that is not this one. Compare that to what we have for our own ocean floor. The best global bathymetric chart, GEBCO, the General Bathymetric Chart of the Oceans, is assembled from a combination of satellite gravity measurements and whatever sonar data has been collected over decades of ship surveys. Its effective resolution across most of the ocean is 5 kilometers, not 5 meters, 5 kilometers. On that map, features smaller than a moderate-sized city are invisible. Underwater mountain ranges appear as smeared gradients. Individual seamounts blur into their surroundings. The detail that the Lunar Reconnaissance Orbiter produces for the Moon in a single orbital pass, resolved, precise, unambiguous, does not exist for the majority of Earth's own surface. The Seabed 2030 project a collaboration between the Nippon Foundation and GEBCO was established in 2017 with the explicit goal of mapping 100% of the ocean floor by the year 2030. When the project launched, approximately 6% of the ocean floor had been mapped to modern standards. By 2023, that number had reached 26%. In 6 years, the project added 20 percentage points. To reach 100%, the remaining 74% would need to be completed in less time than the first 20 took. At current rates, independent analysts conclude the project will not meet its deadline. The ocean is simply too large. The number of ships equipped for high-resolution multi-beam sonar surveys is too small. The funding is insufficient, and the deadline will pass, and the ocean will remain, as it has always been, mostly unseen. There is a phrase oceanographers use with resigned familiarity. We know more about the surface of Mars than the floor of our own ocean. It has become so common, it risks losing meaning, turning from a genuine statement of strangeness into a rhetorical opener, a way to begin a paper or a talk. But the numbers behind it are real, and they're not shrinking. Mars has been mapped by multiple spacecraft over more than 50 years. the Mars Global Surveyor, the Mars Reconnaissance Orbiter, the Mars Express. Together, they have produced maps of the Martian surface at resolutions that, in some areas, approach 25 centimeters per pixel. You can see the tire tracks of the Curiosity rover from orbit. You can follow the path a robot took across the surface of another planet in real time from images taken by satellites with more precision than you can describe the bottom of the Pacific Ocean. The abyssal plains, the vast, relatively flat regions covering most of the deep ocean floor, account for roughly 54% of Earth's total surface area. They are the single largest habitat on this planet. More of Earth's surface is covered by abyssal plain than by all shallow seas, all continental shelves, all land combined. And those plains have been mapped at meaningful resolution, almost not at all. They remain a gravitational inference. We know they are there. We know they are roughly flat. But the specific details, the microtopography, the sediment structures, the biological communities on their surface are unknown across most of their vast, silent expanse. In 2004, a magnitude 9.1 earthquake struck off the coast of Sumatra and generated the deadliest tsunami in recorded history. The earthquake occurred along a subduction zone, a place where one tectonic plate slides beneath another, one of the most geologically violent processes on Earth. Scientists had known this subduction zone existed. They had mapped its general location, but they had not mapped it in detail. They did not have high-resolution images of the seafloor along the fault. They did not know the precise geometry of the rupture zone. The bathymetric data, the depth measurements for that entire region, was so coarse that after the earthquake, when scientists tried to model exactly how the tsunami had propagated, they had to work from incomplete and unreliable figures. The ocean floor beneath one of the most seismically active regions on the planet was, functionally, unknown. The tsunami killed 227,000 people. Part of why the models were imprecise, part of why warnings were slower than they needed to be, part of why the propagation was harder to predict was because the floor of the Indian Ocean was still a blank. Not because mapping it was impossible, because it had never been prioritized. That is not an ancient failure. That is 2004. That is within living memory. And the lesson was noted, and the funding was partially increased, and the surveys expanded, and as of today, that same region of the Indian Ocean remains incompletely mapped. Better than it was, not complete. The moon has no record of Earth's history. It tells us nothing about the evolution of life on this planet, nothing about past climate states, nothing about the biological history of the only inhabited world we know. The ocean floor tells us all of those things. It is a record, a 200 million year archive, accumulated layer by layer in undisturbed sediment chemical signatures of mass extinction events, volcanic winters that lasted decades, the slow rise and fall of species across deep time. The data is there, sealed in the dark and the pressure, patient and complete, and we have read approximately 1/4 of it. The rest is waiting. But here is the deeper question, the one that does not resolve cleanly, that does not close with a satisfying answer. The moon is visible. You can see it from your window on a clear night without any equipment at all. It has been visible to every human who has ever lived since the first eyes opened on this planet. And perhaps that visibility, that constant, luminous presence overhead is part of the answer. We mapped what we could see. We named what was already in front of us. And the ocean kept its own counsel, dark and pressurized and opaque, waiting for us to find a way to look. The question of whether we ever truly will, of whether the technology and the money and the will can be assembled before whatever lies in the remaining 74% is permanently changed by the world above. It belongs to a different part of this story, because before you can understand why we did not look, you have to understand what looking actually requires. And that requires understanding something fundamental about the nature of water itself. Something that makes the ocean, despite being directly beneath our feet, infinitely harder to see than a world 384,000 kilometers away. Light travels 299,792 kilometers per second. In the vacuum of space, that number is essentially absolute. A signal sent from a spacecraft orbiting Mars arrives at a receiver on Earth in somewhere between 3 and 22 minutes, depending on where the two planets are in their orbits. The signal degrades over hundreds of millions of kilometers. It disperses, it weakens, but it arrives. And when it arrives, it carries information, images, elevation data, chemical readings. The light that left a distant surface, or the radio wave that bounced off it, crosses the void and reaches us largely intact. Water does not behave this way. The moment light enters the ocean, it begins to die. Not metaphorically, physically. The water molecules absorb it. The particles suspended in the water scatter it. The deeper it goes, the more of it disappears, wavelength by wavelength, color by color, in a sequence that is slow enough to observe if you dive with a mask and watch the world change around you as you descend. Red vanishes first, within the first 10 meters. Orange follows, yellow. By the time you reach 30 meters of depth, the world around you has turned entirely blue. By 60 meters, that blue is dim. By 200 meters, a depth easily reached by a recreational dive boat, a depth that represents less than 2% of the ocean's average depth sunlight, is functionally gone. What remains is a faint, diffuse twilight that no camera can use to image the seafloor. Below 200 meters, there is nothing. Not dim, not dark, nothing. The ocean floor, at its average depth of 3,800 meters, receives 0 photons from the sunday. It has never, in the history of this planet, been illuminated by anything from above. This single fact makes the ocean fundamentally unlike anything else we have tried to explore. The moon has no atmosphere to scatter light. Point a telescope at it, and the image comes back sharp, clean, resolved, limited only by the optics of your instrument and the stability of the air above you. Mars, even at its farthest point from Earth, can be imaged in extraordinary detail using standard optical telescopes and orbital cameras. Every object in the solar system that we have mapped, every planet, every moon, every asteroid and comet, nucleus, and dwarf world has been mapped using light. electromagnetic radiation bouncing off surfaces and returning to sensors. It is the only method that works at distance, and it is completely, utterly useless in the deep ocean. To see the seafloor, you cannot use light from above. You have to go down there. You have to bring your own light source, lower it to within meters of the seafloor, and look at whatever falls in its beam, which means you can only see what is directly in front of you, an area a few meters wide, illuminated by a small lamp, surrounded on all sides by absolute darkness. It is the equivalent of trying to map a continent by walking through it at night with a flashlight. You will see what is immediately in front of you. The rest of the continent does not exist from your perspective until you walk to it. This is why ocean exploration is so slow. Not because the technology is primitive, because the physics of water makes speed impossible. Every square meter of seafloor that has ever been visually documented was documented by a camera or a human eye that was physically present above it within the range of artificial light, moving at whatever speed the submersible or remotely operated vehicle could manage. The Alvin, one of the most capable deep-sea research submersibles in the world, you can travel several kilometers during a single dive, but its cameras illuminate only a narrow band of seafloor, a few meters wide at any moment. The area it actually documents visually in a single 6 to 10 hour dive is measured in a few hundred square meters at most. One dive, one narrow strip of darkness, briefly lit, then dark again. At that rate, even accounting for improvements in autonomous vehicles, mapping the entirety of the deep ocean floor visually would take longer than the recorded history of human civilization. So we use sound. Sound travels through water the way light travels through space. Not perfectly, not without distortion, but over distances that light cannot reach. Sonar, which stands for Sound Navigation and Ranging, works by emitting acoustic pulses and measuring the time it takes for them to bounce back from the seafloor. The longer the return time, the deeper the water. By sweeping these acoustic pulses across a wide arc below a ship, multi-beam sonar systems can build a three-dimensional map of the seafloor without ever descending to it. This is the technology that has produced everything we know about the shape of the ocean floor. It is powerful, it works, and it has a fundamental limitation that cannot be engineered away. Sound spreads. The moment an acoustic pulse leaves its source, it begins to expand in all directions, losing energy as it does. By the time a pulse has traveled 4 kilometers down to the seafloor and bounced back up, the signal that returns to the ship is faint and dispersed. To compensate, sonar systems use pulses of low frequency, and lower frequencies travel farther through water before dissipating. But low frequency means long wavelength, and long wavelength means low resolution. You cannot resolve features smaller than the wavelength of the sound you are using. A sonar pulse optimized to reach the deep ocean floor and return with useful data cannot resolve features smaller than roughly 50 to 100 meters. That is the hard limit. Not an engineering constraint waiting to be overcome, a consequence of physics. Compare that to the Lunar Reconnaissance Orbiter, imaging the moon at 1 meter per pixel with visible light. The difference is not incremental. It is not a matter of better instruments or more funding. It is a difference in the fundamental physics of the medium. Light in a vacuum travels at the speed of light and carries information at the resolution of its wavelength, which for visible light is measured in nanometers billionths of a meter. Sound in seawater travels at roughly 1,500 meters per second and carries information at the resolution of its wavelength, which for deep penetrating sonar is measured in tens of meters. The ocean does not simply make observation harder. It enforces a physical ceiling on what observation can achieve from the surface. And sonar's problems do not stop at resolution. The ocean is not a uniform medium. Water temperature changes with depth, salinity changes, pressure changes. Each of these variables affects the speed of sound, and because sound speed varies through the water column, acoustic pulses do not travel in straight lines. They bend. The degree to which they bend depends on the specific temperature and salinity profile of the water at that location on that day. An acoustic pulse fired straight down will, in practice, curve slightly sideways as it descends through layers of water with different sound speed profiles. When it returns, the ship's sonar system must correct for this bending, must calculate the actual path the pulse took, rather than assuming it went straight down. Those corrections require detailed knowledge of the water column's temperature and salinity profile, which must be measured separately at the survey site on the day of the survey. If the corrections are wrong, the map is wrong. Seafloor features appear shifted from their true positions. Depths are miscalculated. The map is a map, but it is not quite accurate. This is why bathymetric surveys, even good ones, conducted by skilled teams with modern equipment, require such meticulous work. It is not enough to send a signal and measure the return time. Every aspect of the water column must be understood. Every variable that affects sound propagation must be measured and accounted for. A survey that would be straightforward from orbit point, a camera at the surface, press a button becomes, at the bottom of the ocean, an operation requiring continuous calibration, constant adjustment, and painstaking quality control. The moon has no water column. It has no thermoclines. It has no haloclines. Nothing between the camera and the surface bends the light. What you point at, you see. Now consider the problem of depth itself. Not depth as a number, but depth as a physical environment that destroys things. The Challenger Deep, the lowest point in the Mariana Trench, sits approximately 11,000 meters below the surface of the Pacific Ocean. At that depth, the water pressure is roughly 1,100 times the atmospheric pressure at sea level, 1,100 times. To put that in terms a body can understand, every square centimeter of a vehicle's hull at that depth bears the equivalent of 1,100 kilograms of force pressing inward. An unsupported air pocket at that pressure collapses instantaneously. A human being, unprotected, would not be crushed so much as compressed bones, organs, and tissue, equalizing to the pressure of the surrounding water in ways that are not survivable. Building machines to operate at that pressure requires materials and engineering that are orders of magnitude more demanding than building spacecraft. A spacecraft operates in vacuum, which means zero external pressure. The whole of a spacecraft must contain an internal pressure of about 1 atmosphere, pressing outward against nothing. The hull of a deep-sea vehicle must resist the equivalent of over 1,000 atmospheres pressing inward uniformly from every direction. Titanium, ceramics, glass spheres machined to tolerances of fractions of a millimeter, every seal, every connector, every camera port a potential failure point. One flaw, and the vehicle implodes before its operators above the surface even know something has gone wrong. The engineering challenge is not conceptually difficult, but it is extraordinarily expensive, extraordinarily slow to develop, and extraordinarily unforgiving when it fails. This is why there are fewer than a dozen vehicles in the world capable of reaching the deepest parts of the ocean. Not fewer than a dozen operational ones, fewer than a dozen that have ever been built. The ISS has hosted over 270 people across more than 2 decades of continuous habitation. It is a permanent facility in space, maintained and resupplied on a regular basis, visited by astronauts from multiple nations. There is no equivalent facility on the ocean floor. There is no permanent crewed presence below a few hundred meters depth anywhere at any time. The deepest part of the ocean has been visited by humans only a handful of times in all of history. The first was in 1960, when Jacques Piccard and Don Walsh descended in the bathyscaphe Trieste. The second was in 2012, when filmmaker James Cameron made a solo dive in the Deep-Sea Challenger. Then, in 2019, explorer Victor Vescovo descended multiple times as part of the 5 Deeps expedition, the most systematic attempt yet to reach the bottom of each of the world's 5 oceans. All told, fewer than 20 people have ever been to the deepest place on Earth. Fewer than 20 in all of human history in the deepest place on a planet that is mostly ocean. And yet, the pressure problem is only part of the obstacle. Even if a vehicle can reach the seafloor and withstand the pressure, it must communicate. Acoustic signals, low frequency, low bandwidth, slow are the only reliable communication method through thousands of meters of water. A remotely operated vehicle tethered to a surface ship by a physical cable solves the bandwidth problem, but limits the vehicle's range to the length of the cable and the ship's ability to hold position above it in currents and weather. An untethered autonomous vehicle communicates acoustically, which means data transfer rates measured in kilobits per second, roughly equivalent to the internet speeds of the early 1990s. Sending high-resolution video from the seafloor to the surface is not possible acoustically. The vehicle must store its data internally and return to the surface before its observations can be retrieved. Every dive is a one-way expedition into a communication blackout. What all of this adds up to is an environment that does not merely resist observation. It actively imposes costs on every attempt. Each kilometer of depth adds pressure. Each meter of water removes light. Each degree of temperature difference between water layers bends the sound that carries your data. The tools that work everywhere else, optical telescopes, radio communications, radar, are stripped of their usefulness the moment they enter the ocean. And the tools that do work in water are slow, expensive, limited, and physically fragile in ways that no space-based instrument has to be. The Hubble Space Telescope was launched in 1990. It orbits 340 miles above Earth's surface in the near vacuum of low Earth orbit. It has been observing the universe continuously for more than 30 years, producing images of galaxies billions of light years away with a clarity that no ground-based telescope can match. It has been repaired and upgraded 5 times by spacewalking astronauts. It continues to function today. It was designed, built, launched, and maintained for a total cost of roughly $10 billion over its lifetime. For that same investment, $10 billion, you cannot map the entire ocean floor, not even close. The ships, the vehicles, the personnel, the time, the sheer physical difficulty of moving a sonar-equipped vessel across every square kilometer of ocean at the pace that detailed mapping requires exceeds that budget by a significant margin. The ocean is not expensive to explore because we lack the ingenuity. It is expensive because the physics demand it. Every meter of water is a meter of resistance. The ocean does not yield its information. It holds it under pressure, in the dark, behind walls that cost more to breach than almost anything else humans have tried to breach. There is one more physical constraint worth sitting with, because it is the one that makes the slow pace of ocean mapping feel almost geometric in its hopelessness. A ship conducting a multi-beam sonar survey moves at roughly 10 to 12 kilometers per hour. The speed is limited by the need for the sonar pulses to complete their full round trip to the seafloor and back before the ship has moved. Too far for the return signal to be meaningful. The swath of seafloor a modern multi-beam system can map in a single pass is roughly 2 to 7 times the water depth, meaning in 4 kilometers of water, a ship might map a strip 8 to 28 kilometers wide per pass. That sounds generous until you do the math. The unmapped portion of the ocean floor, 267 million square kilometers, would require a ship moving continuously at survey speed 24 hours a day to travel long enough that the arithmetic becomes difficult to think about clearly. Add weather delays, equipment maintenance, port calls for fuel and supplies, and the number of research vessels in the world equipped for deep-sea bathymetric survey fewer than 40, operating across all the world's oceans simultaneously, and the gap between the task and the capacity becomes something other than a problem waiting to be solved. It becomes a statement about priorities. And here is what that means in practice. Right now, as you listen to this, there are features on the floor of the ocean that are larger than anything visible on the surface of this planet. Mountains, canyons, plains that have not been seen by any instrument, not photographed, not sonared in detail, not visited, simply absent from every map ever made, and we know they are there. Not because we have seen them, because the mathematics of plate tectonics require them. The physics of seafloor spreading demands certain structures exist. The geological record implies their presence. We have inferred them, the way a detective infers a person was in a room from the objects left behind. But inference is not knowledge. Inference is not a map. And for 74% of the ocean floor, inference is all we have. The technology problem is real. The physics problem is real. But neither one fully explains the situation we are in. Because the physics of water have been understood for over a century, the engineering barriers to deep-sea exploration have been known and partially overcome since the middle of the 20th century. The tools exist. Imperfect, slow, expensive, but they exist. Ships are out there right now, sweeping sonar arrays across the seafloor, adding square kilometers to the global map one pass at a time. Progress is real. So why? After a century of knowing what the obstacles are and having at least partial tools to overcome them, has so little of the ocean floor been mapped? Why, in the same decades that took us from the first airplane to permanent residence on a space station, did we leave the floor of our own ocean essentially unexamined? The physics explain why it is hard. They do not explain why we did not try harder. They do not explain why, in the decades that humanity was assembling the most sophisticated technology in its history, the floor of its own ocean was left to its own darkness. A civilization that could build a telescope capable of seeing a galaxy 14 billion light years away could not find the will to look at what lay 2 kilometers beneath the surface of the water covering most of the planet it lived on. That answer lies somewhere else entirely, and it is not the answer most people expect. On the 4th of October 1957, the Soviet Union launched a metal sphere roughly the size of a beach ball into orbit above Earth. It weighed 84 kilograms. It carried no instruments of scientific significance. Its only function was to transmit a radio beep, a steady, repeating signal that anyone with the right receiver could pick up, proving beyond any doubt that the object was up there, circling the planet, doing what no human-made machine had ever done before. The Soviets called it Sputnik. The word means simply satellite, and the moment it cleared the atmosphere, the history of how humanity would spend the next several decades and which parts of its own world it would choose to explore was effectively decided. The United States government's response to Sputnik was not scientific. It was existential. The military implications were immediate and understood by everyone. A nation that could put an object in orbit could put a nuclear warhead anywhere on Earth. The psychological implications were equally clear. The Soviet Union had done something the United States had not. In the Cold War, that gap could not stand. Within a year, the National Aeronautics and Space Administration was established by law. Within 4 years, President John F. Kennedy stood before Congress and committed the United States to landing a human being on the moon before the end of the decade. Not to advance science, not because scientists had identified lunar exploration as a priority, but because it was, in Kennedy's own framing, hard. Because doing it first, and being seen to do it first, would demonstrate something about American capability and American resolve that no diplomatic communique could match. Kennedy's 1,961 speech is remembered as a moment of visionary ambition. And in one sense, it was. The technical challenge it set was genuinely extraordinary. But the urgency behind it was never about science. Kennedy and his advisors were clear, in private and occasionally in public, that the purpose of the moon program was demonstration of American capability, of American resolve. Other frontiers existed. The oceans, their resources and mysteries, were occasionally mentioned in the same breath as space. And then the conversation always returned to space. Because space was the arena where the competition was visible. Space was where the cameras were pointed. Space was where a nation could plant a flag on another world and broadcast the image to every television set on the planet. The ocean floor offered none of that. Whatever you found there, you found in the dark, with no audience and no flag to plant that anyone would ever see. This is the moment the trajectory was set. Not through malice, not through ignorance. Through the specific logic of geopolitical competition, in a world where perception and prestige were as strategically important as military hardware, the moon was a stage, the ocean floor was not. Consider what happened to funding in the years that followed. At its peak in 1966, NASA's budget represented approximately 4.4% of the entire federal budget of the United States, roughly equivalent, in today's terms, to more than $60 billion per year. This was for a single agency, pursuing a single goal, in a program that had existed for less than a decade. The Apollo program alone cost approximately $25 billion in 1960s money, a figure that translates to well over $100 billion today. It employed, directly and through contractors, more than 400,000 people at its height: engineers, scientists, technicians, machinists, seamstresses sewing spacesuits by hand. It was the largest peacetime mobilization of technical talent in the history of the United States. The National Oceanic and Atmospheric Administration, the federal agency responsible for understanding the oceans, did not exist until 1970. It was established 11 years after NASA, 2 years after Apollo 8 sent back the first photographs of Earth rising over the moon's horizon, and in the same year that NASA was already planning for what would come after the moon landings. When NOAA was finally created, its initial budget was a small fraction of NASA's. Today, more than 50 years later, NOAA's annual budget remains roughly 1/4 of NASA's. The agency responsible for the largest ecosystem on this planet, covering 71% of its surface, with jurisdiction over the weather systems that affect every human life, receives roughly 1/4 of the funding of the agency responsible for exploring other worlds. This is not a coincidence. It is the calculus of public attention expressed in congressional appropriations. There is an irony buried in the military history of this period that deserves attention. The United States Navy spent enormous resources during the Second World War and the Cold War, developing acoustic technology for one specific purpose: detecting enemy submarines. Sonar, in its military application, was refined to an extraordinary degree. The Navy built networks of hydrophones across the ocean floor, fixed listening arrays capable of detecting submarine propeller signatures at ranges of thousands of kilometers. These systems, known collectively as SOSUS, the Sound Surveillance System, represented a massive investment in understanding how sound traveled through the deep ocean. The Navy mapped acoustic propagation channels. It cataloged the thermal layers that bend and focused sound. It developed, in short, an intimate knowledge of the ocean's acoustic properties accumulated over decades of classified research, and almost none of that knowledge was applied to mapping the seafloor. The reasons are straightforward in retrospect. Military sonar was optimized to detect things moving through the water column, submarines, ships, the signatures of machinery. Mapping the seafloor required different equipment, different frequencies, different techniques. The knowledge was adjacent, but not directly transferable. And more fundamentally, the Navy had no interest in sharing what it knew. The acoustic geography of the ocean, the precise locations of the channels where sound traveled best, the specific thermal structures that affected detection ranges, was among the most sensitive strategic information the military possessed. Publishing it, making it available to scientists who might share it with foreign colleagues or incorporate it into academic literature that Soviet analysts would read, was out of the question. The deep ocean sat at the intersection of enormous military importance and a complete scientific neglect. The partial declassification of some of this data after the Cold War gave civilian researchers their first access to bathymetric and acoustic records the Navy had accumulated over decades. Scientists were astonished at what had been sitting in classified archives. Data that could have informed ocean science for 40 years had been collected, organized, and filed away where no oceanographer could reach it. When it was finally released, researchers had to revise conclusions based on information that had existed all along, just not for them. The Soviet Union followed a roughly parallel path. Soviet research vessels were active across all the world's oceans during the Cold War, producing substantial bathymetric data and making real contributions to deep-sea science. But the Soviet program, like the American one, was ultimately subordinate to strategic priorities. Data that was strategically sensitive was classified. Missions that served military purposes were funded. Basic ocean mapping for the sake of knowing competed against the same political economy that constrained it in the West. Neither side ever made the seafloor a priority. Understand what drove that calculus. Space exploration produced images. The Earthrise photograph, taken by Apollo 8 astronaut William Anders in December 1968, is widely considered one of the most influential photographs ever taken. A small blue planet, impossibly fragile, suspended in absolute blackness. It changed how people thought about the Earth. It contributed directly to the environmental movement. It is a photograph that everyone who lived through that era remembers. NASA was extraordinarily good at producing images of rockets launching in columns of fire, of astronauts floating in the void, of the lunar surface stretching away in all directions under an unblinking Sunday. Every mission was a spectacle. Every mission produced something to show. Deep-sea exploration produced nothing comparable. The first photographs from the deep ocean floor were taken in the 1950s, and they showed a flat, gray, featureless plain. Marine snow drifting downward, sediment. In some cases, complete darkness, because the cameras had not descended far enough or the lights had failed. There was no drama visible in those images, no color, no scale that a human eye could intuitively grasp. When scientists came back from deep-sea expeditions with data sonar profiles, sediment cores, temperature measurements, they had numbers, graphs, curves on paper. They did not have something you could broadcast on the evening news. Jacques Cousteau changed that partially. Beginning in the 1950s and accelerating through the 1960s and 1970s, Cousteau brought the shallow ocean to mass audiences through film and television. His series, The Undersea World of Jacques Cousteau, ran for a decade. It was watched by hundreds of millions of people. It made the ocean beautiful, colorful, mysterious, alive. Cousteau was a genuine explorer and a genuine communicator, and his work did more to build public affection for the ocean than any scientific institution had managed before or since. But Cousteau worked in the shallow ocean, the sunlit zone, the coral reefs, the kelp forests, the coastal waters where light still penetrated and cameras could capture color. The deep ocean, the dark ocean, the ocean below 200 meters where the floor actually lay that remained outside his reach and outside his frame. The deep sea could not be filmed the way Cousteau filmed his world. It had no color. It had no sunlight. Its creatures were adapted to darkness and, when brought to the surface, died or decomposed beyond recognition. The deep ocean offered nothing that fit the visual grammar of the nature documentary. So the public developed a profound love of the ocean's surface and essentially no awareness of what lay below it. This asymmetry between public attention and scientific importance is not unique to oceanography, but it played out with unusual severity in the case of the deep sea. Every dollar appropriated for NASA was a dollar that politicians could point to launches, photographs, astronauts, national pride. Every dollar appropriated for deep-sea research produced a sediment core that went into a refrigerated archive, a sonar track that went into a database, a paper published in a journal that almost no one outside a field would read. The political economy of science funding strongly favors the visible, and the deep ocean is definitionally invisible. There is a document that almost no one outside science policy circles has ever read. In 1969, a commission established under President Lyndon Johnson published a report concluding that the United States was dramatically underinvesting in ocean research relative to its importance. It recommended a national ocean agency with resources comparable to NASA. The following year, under President Nixon, NOAA was created. The report has been largely forgotten. NOAA's budget was set far below what the commission recommended. Apollo succeeded. The moon landings ended. The window of political urgency closed. The ocean report had produced a bureaucracy, but not a mission, not a Kennedy moment, not a commitment that captured public imagination and held it across decades. Kennedy's commitment to the moon produced Apollo. That report produced NOAA. The difference in scale between those two outcomes is a precise measurement of how the political economy of that era valued space versus ocean. And that valuation has never been fully corrected. This is not entirely the story of government. Private interest has followed the same pattern, and for similar reasons. The space industry, rockets, satellites, eventually crewed commercial vehicles, has attracted enormous private investment because space offers things that investors and entrepreneurs find compelling. Communication satellites generate revenue. Earth observation satellites generate revenue. The prospect of asteroid mining, of lunar resources, of Mars colonization, these attract capital because they attach to a vision of expansion, of new frontiers, of the kind of transformative economic opportunity that investors are trained to seek. The ocean floor has not attracted comparable private investment because the ocean floor offers nothing that translates easily into a business model that conventional investors recognize. The minerals are there. The hydrothermal vent systems produce heat that could theoretically be captured, but reaching them in the dark, under crushing pressure, with no communication and no reliable infrastructure, the return on investment calculation has never, for most of the past century, worked in the ocean's favor. There is one exception, and it is instructive. The deep-sea mining industry has been developing, slowly and controversially, for decades. Polymetallic nodules, potato-sized lumps of manganese, nickel, cobalt, and copper that litter large areas of the abyssal plains represent deposits of critical minerals that land-based sources cannot easily supply. As demand for those minerals has grown, driven by the expansion of battery technology and renewable energy infrastructure, the economic argument for mining the deep seafloor has strengthened. Companies have spent billions of dollars developing equipment to collect these nodules from depths of 4 to 5 kilometers. The International Seabed Authority, a UN body, has issued dozens of exploration licenses covering millions of square kilometers of ocean floor. And here is what makes that development so strange, viewed against the backdrop of this story. The companies seeking to mine the ocean floor know more about the specific areas they intend to mine than any government-funded ocean research program has mapped in equivalent detail. Commercial interest, when the business case is strong enough, does what government scientific interest did not. It maps. It surveys. It invests in the detailed knowledge of the seafloor that centuries of scientific underfunding never produced. The ocean floor may ultimately be mapped not by researchers driven by curiosity about what is there, but by engineers calculating how much of it can be extracted. That possibility that the first comprehensive map of the ocean floor might be produced by the mining industry as a byproduct of resource extraction says something about the priorities that shaped this history. The ocean was not explored because people wanted to know what was there. It was left unmapped because knowing what was there was never, in itself, valuable enough to justify the cost. That calculation is changing, but it is changing for reasons that have very little to do with the spirit that sent ships to the moon. What neither side ever did, what no government in the Cold War era, East or West, ever committed to, was a systematic, comprehensive program to map the ocean floor as a scientific end in itself. The moon got that commitment. The ocean never did. And when the Cold War ended, and the political urgency that had driven space funding dissipated, there was no equivalent moment of clarity about the ocean. No president stood before Congress and said, "We will map the floor of our own ocean before the end of this decade." The comparison was made by scientists, occasionally, in papers and congressional testimony. It did not produce anything resembling a national commitment. NOAA exists. It funds research. It operates ships. Over 50 years, it has contributed to the incremental progress that has brought ocean floor mapping to its current state. But it has never had a mission equivalent to Apollo. Apollo had a date, a destination, a person standing on another world holding a flag. Noah has a mandate to understand and steward the ocean, important, necessary, and almost completely impossible to fit into a photograph. This is the inheritance of those early choices. Not just the underfunding, though the underfunding is real. The deeper inheritance is the absence of a narrative. Space exploration has a story almost every person alive can follow. Rockets, astronauts, planets, the black infinity between them. Ocean exploration has sediment cores, sonar tracks, papers on benthic community structure. It has Jacques Cousteau, who filmed coral reefs, not the abyssal plain. It has the Titanic, which captured the world's imagination as a shipwreck, not as evidence of how little we knew about the seafloor surrounding it. The story of the deep ocean has never been told in a way that made large numbers of people feel they needed to know it. Money follows attention. Attention follows stories. And the story of what lies in the darkness below the ocean has, for most of the past century, been told to almost no one. What was down there all along, while humanity looked upward and outward, is a question that the next part of this story begins to answer. And the answer is stranger and more consequential than the question implies. In February of 1977, a group of geologists aboard the research vessel Knorr lowered a temperature probe into the water above the Galapagos Rift, a section of the mid-ocean ridge system running along the floor of the eastern Pacific. They were not looking for life, they were looking for heat. The geological models of the time predicted that seawater, percolating down through cracks in the newly formed ocean crust, would be heated by the magma below and return to the seafloor slightly warmer than the surrounding water. They expected to find a gentle thermal anomaly, a few degrees above ambient, geologically interesting, biologically irrelevant. The probe found a temperature spike of several degrees. The scientists redirected the submersible Alvin to investigate. What they found when they arrived at the source of that heat has been described by the people who were there as the most shocking moment in the history of marine biology. The seafloor around the vents was not bare rock. It was alive, not sparsely, not marginally explosively, riotously, in densities of life that should not have been possible in a place with no sunlight, no photosynthesis, and no connection to the surface food web. Tube worms 2 meters long clustered around the vent openings, their plumes bright red in the submersible's lights. White crabs moved through forests of the tube worms. Clams the size of dinner plates sat in dense clusters on the basalt. Pale fish hovered in the warm water above the vents. It looked like a coral reef, in terms of biological density and structural complexity, except that it existed in complete darkness, under 2 kilometers of water, in a place that the existing science of the time said should have been as lifeless as the lunar surface. The discovery forced an immediate and fundamental revision of one of biology's oldest assumptions. For the entire history of the science of life, photosynthesis had been understood as the base of every food chain that mattered. Sunlight hits a plant or an alga, which converts it into organic carbon which feeds the animals that eat the plant, which feed the animals that eat those animals, and so on through every ecosystem on Earth. Sunlight was not simply important to life, it was, in the understanding of that time, the prerequisite for life. Nothing could grow without energy from the sun, and nothing could get energy from the sun in the absolute darkness 2 kilometers below the ocean's surface. The tube worms around the Galapagos vents had not read that assumption. Their bodies contained no chlorophyll. They had no digestive system in the conventional sense. What they had, what most of the organisms in that vent community had, was a symbiotic relationship with bacteria that derived their energy not from sunlight, but from the chemical reactions produced by the vent fluid itself. The water pouring out of those hydrothermal vents was rich in hydrogen sulfide, a toxic compound that most surface life cannot tolerate. The bacteria around the vents used hydrogen sulfide as an energy source, the way plants use sunlight. They oxidized it and captured the energy released. The tube worms housed these bacteria in a specialized organ and fed off the organic carbon the bacteria produced. The clams did the same. The entire ecosystem ran on chemistry, not light. This process, chemosynthesis, had been theorized but never observed at scale before February 1977. The implications took years to fully absorb. If life could build an entire ecosystem around chemical energy deep in the ocean, with no connection to the sun whatsoever, then the range of environments where life could exist was dramatically larger than anyone had assumed. And if the range of environments on Earth where life was possible was dramatically larger, then the range of environments elsewhere in the universe where life might be possible was also larger. Hydrothermal vent systems, as it turned out, do not require a planet with sunlight, a surface, or an atmosphere. They require only liquid water and geological activity. Both of those conditions are known to exist on worlds far from Earth. That connection, from a temperature spike on the Galapagos Rift in 1977 to revised estimates of life's distribution in the universe, was not obvious at the time. It became obvious slowly as further expeditions returned with further evidence of what the deep ocean contained. Because the Galapagos Rift was not the last vent system found. It was the first. In the decades that followed, hydrothermal vent communities were discovered along mid-ocean ridges across the Pacific, the Atlantic, and the Indian Ocean. Each new system brought new species, new chemistries, new architectural forms of biological community. Some vent systems produced the classic black smoker structures, chimneys of precipitating minerals, rising meters above the seafloor, pouring superheated water that reached temperatures of over 400 degrees Celsius. Others were cold seeps, where methane-rich water oozed through the sediment and supported communities built on methane-oxidizing bacteria. Still others were entirely novel in structure and chemistry, fitting no category that existed before they were found. In the year 2000, a scientific expedition stumbled across a vent system unlike anything previously described. It was located on an undersea mountain called the Atlantis Massif, rising from the floor of the mid-Atlantic Ocean. The vents there were not the sulfide chimneys of the Pacific systems. They were white, towering structures of carbonate minerals, some of them rising 60 meters above the seafloor, taller than a 15-story building, formed not by volcanic heat, but by a chemical reaction between seawater and the exposed mantle rocks of the ocean floor. The scientists named the field Lost City. The organisms living there were unlike those at the black smoker systems, drawing energy from hydrogen gas produced by the rock-water reaction rather than from hydrogen sulfide. Lost City was not a variation on a known system. It was a new category of environment that no one had predicted, discovered in the middle of an ocean that had been crossed by ships for 500 years. Lost City exists on the Atlantis Massif. The Atlantis Massif is not obscure or remote. It lies in the central Atlantic, not far from the mid-Atlantic ridge that has been known to scientists since the 1950s. For decades, ships passed over it or near it. Nobody found Lost City because nobody was looking closely enough with the right instruments at the right depth. The system almost certainly has equivalents elsewhere on the ocean floor, other carbonate vent fields, other serpentinite-hosted ecosystems, other variants of the Lost City type that have not been discovered yet because the ocean has not been searched for them. The question is not whether such systems exist. The question is how many there are and what they contain. Every significant expedition to an unmapped region of the deep ocean has returned with new species. Not occasionally, every time. The rate of species discovery in the deep sea, despite the extraordinary difficulty and expense of each expedition, has not slowed as exploration has continued. If anything, the rate suggests the scope of what remains undescribed. Conservative estimates suggest that the deep ocean harbors somewhere between 500,000 and 10 million species that have not yet been named by science. The range of that estimate, 500,000 to 10 million, is itself revealing. When the uncertainty in a scientific estimate spans an order of magnitude, it is because the underlying data is nearly absent. We do not know how many species live in the deep ocean to within a factor of 20 because we have barely looked. What we have found and the looking we have done consistently defies expectation. In 2022, scientists mapping a section of the Pacific Ocean floor near the remote Clarion-Clipperton Zone, an area of abyssal plain being assessed for deep-sea mining, documented more than 5,000 species in their samples. Of those 5,000, approximately 90% were previously unknown to science. 90%. In a single survey of a single region of the ocean floor. The Clarion-Clipperton Zone covers roughly 6 million square kilometers, an area larger than the continental United States. The survey covered a fraction of that area, and 90% of what it found was new. This is not the kind of finding you expect in a supposedly well-studied part of the planet. Scientists have been cataloging Earth's species for 3 centuries. By the late 20th century, the broad outlines of life on the land surface were thought to be reasonably well understood, not complete, not exhaustive, but not likely to produce surprises of the first order. The deep ocean has not reached that point. It has not come close to that point. It is not approaching that point. Every time a camera descends to a region that has never been visited, it finds organisms that no one knew existed, doing things that no existing model predicted in quantities that no prior survey suggested were present. In 2020, researchers exploring waters off Western Australia documented a siphonophore, a colonial organism made up of thousands of individual creatures functioning together as a single animal, appearing to be approximately 45 meters long. It would be the longest animal ever recorded. It was found not in some remote trench, but in the waters off a continent inhabited for 60,000 years. Nobody had seen it before because nobody had looked at that depth in that layer of the ocean with those instruments. And here is what connects all of these findings. The tube worms of 1,977, the white towers of Lost City, the 5,000 Clarion clipperton species, the siphonophore off Australia. Each of them was found in a part of the ocean that, until the moment of discovery, appeared on every existing map as blank, not labeled unknown, not marked unsurveyed. Simply absent a region where the available data said nothing because no one had collected data there. The gap was not between known and uncertain. It was between absent and extraordinary. And the pattern extends further than any of those individual discoveries suggest. Consider what the trenches alone have yielded. The Haddle Zone, the name given to ocean depths below 6,000 meters, found almost exclusively in the Great Oceanic Trenches, was long assumed to be among the most hostile environments on Earth. The pressure at those depths is sufficient to compress the molecules of living tissue to the point of dysfunction. Temperature hovers near freezing. There is no light, no organic matter raining down from above in any quantity that seems sufficient to support a meaningful community of organisms. For most of the 20th century, the trenches were treated as the biological equivalent of a desert, places where life might cling on in minimal form but could not truly flourish. Then people actually went there and looked. The Mariana Trench, the deepest point in the ocean, has now been visited by camera-equipped vehicles on multiple occasions, and each visit has produced organisms that were not predicted to be there. Amphipods, small crustaceans resembling shrimp, exist in the trench in such density that they can be caught in traps by the thousands. They are not struggling to survive in minimal form. They are abundant. Sea cucumbers have been found at depths exceeding 10,000 meters, moving across the sediment in apparent health. Snailfish, small, translucent, gelatinous-looking fish, have been filmed at depths that, until relatively recently, scientists believed no vertebrate could survive. In 2023, a snailfish was filmed at approximately 8,336 meters in the Izu Ogasawara Trench, the deepest fish ever recorded. It was not barely alive. It was swimming, foraging, behaving like a fish. The organisms that live in the Haddle Zone have not simply tolerated conditions that should be lethal. They have adapted to them with a precision that took millions of years to develop. Their cell membranes contain different molecules that remain fluid under crushing pressure. Their enzymes fold and function at pressures that would destroy the proteins of a surface animal. The Haddle Zone did not stop life. It shaped it, producing organisms built specifically for the crushing dark at the bottom of a trench. Organisms that exist nowhere else. Organisms that, before humans descended to observe them, were completely unknown. there are 37 trenches in the world's oceans. Of those, only a small number have been visited by camera-equipped vehicles. The rest remain visually unexplored, their floors unobserved, their communities undocumented, their species uncounted. Given what has been found in the trenches that have been visited, the assumption that the unvisited ones will prove less interesting seems optimistic. Each visited trench has returned findings that revise the prevailing model of what deep trenches contain. There is no obvious reason to expect the unvisited ones to be different. The trenches are not the only unexpected habitat. Deep-sea coral reefs, structural communities built by cold-water corals growing in complete darkness, at temperatures near freezing, hundreds to thousands of meters below the surface, were long considered minor curiosities. The vibrant, sunlit shallow water reefs were the ones that mattered ecologically and commercially. Cold water corals were occasional finds, fragments dredged up incidentally during other surveys, growing slowly on seamounts and continental slopes. Not until researchers began systematically exploring the deep continental margins with modern cameras did the scale of these communities become apparent. Cold water coral reefs now appear to be among the most structurally complex ecosystems in the deep ocean. Some systems extend for hundreds of kilometers along continental margins, rising meters above the seafloor in branching architectures that provide habitat for hundreds of associated species. The largest known cold water coral reef system lies off the coast of Norway, extending approximately 35 kilometers, hosting a community as diverse as any tropical reef. It was not known to science in its full extent until the 1990s. Similar systems have since been found off Ireland, Scotland, the United States, Canada, Brazil, and Australia in nearly every deep water region that has been carefully examined. Each one was found by going somewhere with a camera and looking. The rate at which new species appear in deep-sea samples has resisted the usual pattern of scientific discovery, where early exploration yields the most dramatic findings and later work fills in details. In most environments, the new species rate declines as characterization improves. In the deep ocean, it has not. The pipeline of undescribed specimens already collected organisms sitting in museum jars, not yet formally examined, is large enough to occupy the global community of deep-sea taxonomists for generations. And that backlog was generated by the small fraction of the deep ocean that has actually been visited. Since the discovery of hydrothermal vents in 1977, over 700 distinct vent sites have been documented across all the world's oceans. Each newly discovered site has introduced new species. Some have introduced new genera. A handful appear to represent entirely new branches of the tree of life, quietly growing in the dark while biology assembled its picture of life's diversity from the sunlit surface above. 700 vent sites. The global mid-ocean ridge system stretches for 65,000 kilometers. 700 known sites along a chain 65,000 kilometers long. The math is not reassuring. If the known sites were distributed evenly, which they are not, because discovery is a function of where surveys have been conducted, not where vents exist. Each known site would represent roughly 90 kilometers of ridge, 90 kilometers of unexplored volcanically active ocean floor between each documented site. And the distribution is not even. Large sections of the mid-ocean ridge, particularly in the Southern Ocean and parts of the Indian Ocean, have been surveyed only superficially. The ratio of what has been found to what could exist does not suggest the catalog is nearing completion. It suggests the catalog has barely begun. That is the dislocation at the center of this story. Not just that we have left most of the ocean unmapped, but that the part we have mapped has revealed, consistently and repeatedly, that the unmapped part is more surprising than we assumed. The predictions made before each new survey have been wrong. Not slightly wrong, categorically wrong. The map keeps getting stranger at its edges, and 74% of it has no edges, yet no surveys, no cameras, no names for what lives there. There is a question buried inside every discovery the deep ocean has produced, one that the scientists who make those discoveries rarely ask out loud, because it is not the kind of question that fits in a grant proposal or a peer-reviewed paper. It is not a question about data. It is a question about us, about the kind of animal that builds telescopes powerful enough to resolve the surface of a planet in another solar system, then leaves the floor of its own ocean unmapped for a century and a half, about what it means to look everywhere except down. The psychological pull of space is not hard to understand. Humans evolved on a surface, a flat, sunlit, horizontal plane, where vision was the dominant sense, and distance meant safety or opportunity. The sky was always visible. It was a source of warmth, of weather, of the rhythms of night and day that organized everything. Long before anyone understood what the stars were, they were points of reference, navigational anchors, calendrical markers, objects of wonder that required no instrument to perceive. The impulse to know what they were is not culturally specific. It appears in every human civilization ever studied. The sky was always there, always visible, always inviting interpretation. Looking upward is, in some sense, the most natural thing a human brain does. The ocean is different. The ocean's interior is invisible by design. You cannot look into it the way you look into the sky. You can look at it at its surface, at its color, at the way it moves, but the moment you try to look into it, it refuses. It scatters and absorbs the light that would carry information. It hides its own contents behind a barrier that human senses cannot penetrate and that human technology only partially overcomes at great expense and effort. The ocean is not inviting. It does not beckon the way a horizon does. It presents a surface that ends inquiry rather than initiating it. And below that surface, the qualities that make the deep ocean scientifically extraordinary are the same qualities that make it psychologically oppressive. It is dark in a way that no surface environment is dark, a darkness so complete that the concept of vision stops applying. It is pressurized in a way that excludes the human body by design. It is cold. It is vast. It has no exits. A person in the deep ocean is enclosed on all sides by a medium that does not support human life, cannot be traversed without machines, and offers no visible horizon, no sky, no reference point that a human nervous system is built to orient by. The deep ocean is, in an almost literal sense, the opposite of the sky. This is not a small thing. The environments where humans feel most alive, open landscapes, mountain summits, starry nights, the view from altitude share a quality of expansiveness, of possibility, of a horizon that implies continuation beyond what can be seen. The deep ocean offers none of this. It offers confinement, darkness, pressure, cold, and a silence so complete it registers as a kind of presence rather than an absence. The few people who have descended to the deepest parts of the ocean and come back to describe the experience have not, typically, described it as beautiful. They have described it as alien, as profoundly, unsettlingly other. Not the way the moon is other remote and austere, but geometrically familiar, lit by the same sun, visible from Earth on any clear night. The deep ocean is other in a way that pulls against the grain of what a human brain is built to tolerate. And yet it is here. It is not somewhere humanity must journey to at great expense and risk. It is covering 71% of the surface of the planet we live on, beginning a few meters below the surface of water that humans have been swimming in for as long as our species has existed. The distance between the familiar world and the utterly alien one is not 384,000 kilometers. It is a few hundred meters of water. The difference in how the human mind responds to those two distances is not rational. Rationally, the closer unknown should attract more attention. If curiosity is proportional to proximity, the deep ocean should have been explored before any spacecraft left the atmosphere. The fact that it was not that a civilization chose to reach for the moon before it chose to descend to its own seafloor points to something that cost-benefit analysis cannot fully account for. It points to the psychology of looking. Human vision evolved for a sunlit, open environment. The structures of the eye, the organization of the visual cortex, the neural circuitry that processes spatial information, all of it calibrated to a world of light, color, depth cues, and horizon. The brain is not a neutral processor of sensory information. It is a prediction machine, constantly generating models of what the environment will look like a moment from now, calibrated by millions of years of experience with sunlit landscapes. When vision fails, when light is removed, and the prediction machine has nothing to work with, the response is not neutral either. It is anxiety. It is the activation of threat response systems that evolved precisely because darkness in the ancestral environment meant danger. The deep ocean is dark in a way that is not merely inconvenient. It is dark in a way that speaks directly to the oldest layers of the brain in a register that is not entirely rational. That proximity is, perhaps, part of the problem. Space is sufficiently far away that it can be approached as an adventure, as a deliberate departure from the familiar, undertaken with preparation and intention, and the psychological protection of knowing that the familiar world still exists and can be returned to. The deep ocean is too close for that framing. It sits beneath the surface of the ocean that cargo ships cross, that fishing trawlers work, that recreational swimmers enter without a second thought. The alien world is right there, adjacent to the ordinary one, separated only by depth. There is no comfortable distance from which to approach it. It is simply underneath. And inside that underneath, as nearly 5 decades of increasingly capable observation have demonstrated, is a record that the surface world badly needs to understand. The ocean does not merely cover the planet, it regulates it. The deep ocean circulation system, the slow movement of cold, dense water from the poles to the tropics and back, driven by differences in temperature and salinity, taking centuries to complete a single cycle, distributes heat across the globe in ways that determine climate at every latitude. The carbon cycle that keeps atmospheric carbon dioxide at levels compatible with the civilization humanity has built runs, in large part, through the ocean. Phytoplankton at the surface fix atmospheric carbon through photosynthesis. When they die, some of that carbon sinks to the deep ocean in what oceanographers call the biological pump, removing it from the atmosphere for centuries or millennia. The chemistry of the deep ocean, its temperature, its pH, its dissolved oxygen content, determines how efficiently this pump operates. We do not fully understand how the deep ocean circulation system works. We do not have adequate maps of the seafloor features that shape it, the ridges, the fracture zones, the seamounts that deflect and redirect the deep currents. We do not know how the system will respond to the warming that is already occurring at the surface. We know that it has changed before that past climate transitions involved dramatic reorganizations of deep ocean circulation that produced rapid, planet-scale shifts in temperature and precipitation. We know that the current trajectory of surface warming represents an experiment on a system we do not fully understand, with consequences that our models cannot accurately predict, partly because the physical geography of the ocean floor that shapes those models is incompletely known. Consider the Atlantic meridional overturning circulation, the system that moves warm surface water northward from the tropics and returns cold, dense, deep water southward in a loop that takes roughly 1,000 years to complete. This system is, among other things, responsible for the relatively mild climate of Western Europe. London is at roughly the same latitude as parts of northern Canada. The reason London has a temperate climate while those Canadian latitudes are defined by permafrost is the AMOC, the steady transfer of tropical heat northward by the ocean's circulation. Multiple studies published in recent years have found evidence that the AMOC is weakening. Some analyses of deep ocean sediment cores suggest it may be approaching a tipping point beyond which the current could slow dramatically or collapse. The consequences of such a collapse for European climate, for monsoon systems that feed billions of people in Asia and Africa, for the ice sheets of Greenland and Antarctica would be severe. The models that attempt to project when and whether such a collapse might occur depend on an understanding of the deep ocean that is incomplete. The seafloor features that constrain the circulation are not fully mapped. The deep sediment records that might reveal how quickly the transition could occur have not been fully retrieved or analyzed. We are trying to predict the behavior of a system whose physical structure we have not yet described. This is not abstract. The ocean is absorbing more than 90% of the excess heat being trapped by the atmosphere. It is absorbing roughly a quarter of the carbon dioxide humanity is emitting. Without the ocean, the planet would already be several degrees warmer than it is. The ocean is buffering the worst consequences of what humanity is doing to the atmosphere at a cost to itself that includes acidification, deoxygenation, and warming that affect the ecosystems living in it. We are asking the largest, least understood system on the planet to protect us from the consequences of our own behavior without having taken the trouble to understand how that system works. And the deep ocean, the part we have not mapped, is where much of the buffer operates. The cold, dense, deep water. The abyssal sediments. The biological communities at the bottom of the biological pump. The circulation system whose pathways follow contours of the seafloor that we have not drawn. We are relying on mechanisms we cannot fully describe, operating in spaces we have never seen to maintain the conditions that allow the civilization we have built to continue functioning. The urgency of understanding the deep ocean is not merely scientific. It is the urgency of understanding the life support system of the only inhabited planet we know of, before the conditions it has maintained for 10,000 years of human civilization cease to be stable. There's one more dimension to this that the science of the past 50 years has opened, and that the discoveries in the deep ocean have made impossible to ignore. Chemosynthesis, the process discovered at the Galapagos Rift in 1977, means that life does not require sunlight. It requires chemistry and energy, and those can be supplied by geological processes that have nothing to do with a star. Hydrothermal vents operate wherever liquid water meets geological heat. That combination exists, as best current evidence suggests, in the subsurface oceans of Europa, Enceladus, and possibly several other moons in the outer solar system. The ocean hidden beneath Europa's ice shell may be in contact with a rocky seafloor heated by tidal forces. Enceladus is actively venting water vapor into space, a process that requires liquid water in contact with hot rock below. Both of those environments are structurally analogous to the conditions in which the Galapagos vent communities were found. Before 1977, the search for life elsewhere in the solar system was essentially a search for planets with sunlight, liquid surface water, and moderate temperatures. Mars was the primary candidate. The discovery that life could run on chemistry instead of light expanded the list of candidates to include worlds that receive almost no sunlight at all, buried under kilometers of ice in the cold outer reaches of the solar system, where no one had previously looked for life. The deep ocean, by demonstrating what life was capable of on this planet, fundamentally changed the question of what life might exist elsewhere. That change began in the dark, 2 kilometers below the surface of the Pacific, in February 1977. This is the full scope of what it means that we have left 74% of the ocean floor unseen. Not just the species we have not counted, or the geological systems we have not described, or the chemical processes we have not characterized, but the information about how this planet sustains itself that we do not have. The template for life in other oceans in the solar system that we have not completed. The record of Earth's climate history encoded in sediment layers that we have not read. The understanding of what we are doing to the ocean and what the ocean, in consequence, may stop doing for us that we do not yet possess. Before any of this can be fully understood, the circulation, the chemistry, the biology, the geological record, the implications for life elsewhere, something simpler has to happen first. The ocean has to be seen, not sampled, not inferred, not modeled from gravitational anomalies detected by satellites. Seen. The physical reality of what the ocean floor looks like, what structures it contains, what communities live on it, what chemical processes drive those communities, that foundational information, the equivalent of what a photograph is for the surface of the moon, has not been obtained for 74% of the ocean. Everything else that scientists want to know about the deep ocean depends on information that has not been collected yet. This is an unusual situation in science. In most fields, the frontier is at the edge of what is known new measurements at higher precision, new tests of established theories, new data that refines existing models. In deep ocean science, the frontier is not at the edge of what is known. It is at the near end of what is unknown. The basic map has not been made. The inventory has not been taken. The catalog of what exists is nowhere near complete. The situation is not that we know the deep ocean and are trying to understand it better. The situation is that we do not know what is there. And until we look, we are working in a vacuum that no amount of theoretical sophistication can fill. You cannot model what you have not seen. The ocean has been here for 4 billion years. It has survived every mass extinction this planet has experienced. It has persisted through snowball glaciations when ice covered the equator, through greenhouse intervals when the poles were tropical, through the asteroid impact that ended the dinosaurs, through every catastrophe that wiped out most of what lived at the surface. It will persist through whatever we do to it, now changed, diminished in the diversity that 10,000 years of human civilization has come to depend upon, but persistent. The ocean does not need us to know it. It was doing what it does long before any eyes existed to observe it, and it will continue long after. What we need, perhaps, is to know it, not for the ocean's sake, for ours. We have spent the past century learning more about the surface of other worlds than about the floor of this one. That choice is not irreversible. The technology exists. The ships can be built. The vehicles can be improved. The mapping, if sustained and adequately funded, can be completed within a generation. The species can be counted, the vent systems cataloged, the sediment cores retrieved, the circulation system mapped in the physical detail it requires. None of this is beyond the reach of a civilization that has placed telescopes in orbit and sent probes to the edges of the solar system. The will, the collective decision that this is worth doing, that the largest unknown on the planet we live on deserves the sustained attention of the civilization that depends on it, is the one thing that has not yet arrived in sufficient force. Perhaps it will. Perhaps the urgency of what the ocean is absorbing on our behalf will concentrate the attention that curiosity and wonder on their own have not managed to sustain. The ocean is waiting. It has always been waiting. Every meter of it, every kilometer of dark and pressure and chemical improbability, every trench and ridge and carbonate tower and abyssal plain, all of it waiting, as it has always waited, entirely indifferent, to whether the eyes that have been looking everywhere else ever choose to look down. The ocean does not need to be found. We are the ones who need to find it. If this journey moved something in you, consider subscribing to Sleep on Deep. Every week, we descend a little further. The ocean is waiting.